Hi everyone, welcome to GEMCHEM. Now today's video is on Stereochemistry part 10 video, and here we are going to deal with topicity and Prostereoisomerism. Now before starting, already 9 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GEMCHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So two groups or two atoms are considered to be homomorphic if they are connected in isolation to each other. Suppose take this as an example, that is this molecule. So here when we are talking about homomorphic, then HA and HB are connected in isolation to each other, as a result of which we can say that they will exhibit topicity, and topicity is of two types, homotopic and heterotopic. Already one video on topicity is done in the channel. You can watch it. I will give the link in the description box as well as the I button present above this video. So when we are seeing this HB and HD, these are not constitutionally same, whereas when we talk about HF and HB, these two are having same groups around them. As a result, we can conclude them as constitutionally same type of groups. So these are the two kinds, and here we are going to see that how can we determine the topicity. Two methods to determine the topicity will be your substitution or addition, and another will be based on symmetry. So the same molecule we are going to consider this one and see the difference in the topicity. So first we have taken this and we are going to see how to substitute. So what we are going to do is we are compressing this whole structure as C3H7, and we will see the topicity of HA and HB. We are going to substitute HA by X and HB also by X and see the relationship between the two compounds present. Remember that X should never be any group or atom connected to the center to which this homomorphic group is being already attached. So here we can see that we are getting a mirror image relationship. Similarly, we can see here that these are known as enantiomers. So these two hydrogen atoms are enantiomeric or enantiotopic. So HA and HB can be concluded as enantiotopic. Next we are going to see that we will replace another two hydrogens with X. So what we have done is we have compressed the upper part and the lower part, and we are going to see the relationship between HC and HD. So in this case also, if you try to do homotopic, because once you rotate the molecule, again the same molecule will be obtained. So two homomorphic ligands, atoms or groups are interchanged by Cn, then we can say this is homotopic, since you can rotate it by 180 degree, that is C2 axis, to get the same hydrogen in the same place, as a result of which we can conclude that these are homotopic hydrogens. Two homomorphic ligands that can be interchanged by sigma, I, Sn are enantiotopic, and when they are non-interchangeable, that is they are not mirror image of each other or they don't have an axis of symmetry, they are known as diastereotopic. See our first example. So this one, if you consider, you can see CH3 present. As a result, here there will be a C2 axis, and presence of C2 axis hints that these two hydrogens will be my homotopic hydrogens. Now let us go for the next molecule. So if we consider this one, the two hydrogens for which topicity is being considered is these two circled in greens. So here only you can see that there is a C2 axis, and since there is a presence of C2 axis, so this hydrogen will have homotopicity. If we see some more examples, for this one you can see here that there is no axis of symmetry. Okay, axis of symmetry means that there will be no CN. And if you consider one hydrogen is cis to your CH3, one hydrogen is trans to your CH3. As a result, this can be concluded as diastereotopic. If we go for the next one, next molecule, then you can consider here HA and HB, this two. If you see or exchange them by substitution, then they can be concluded as enantiotopic. Similarly, HC and HD are enantiotopic. So write down HA and B and HC and D are your enantiotopic. Similarly, if you go for the next one, that is HA and HC, then also they are enantiotopic. Also your HB and HD is enantiotopic, these pairs. And the last one which is left with you is HA and HD. So when we are considering HA and HD, this one will be your homotopic, because these can be exchanged by symmetry axis. Okay, so we have 5 pairs and 5 relationship in a particular molecule. Next one will be this example. So you can see that the hydrogens present in the OH group will be our main thing to be determined. So for the H, these H can be rotated by using CN axis. As a result, these are homotopic in nature. Next one is COOH group in the different molecule. So these COH are enantiotopic in nature. This is our next molecule where we can see that the 2 hydrogens are present, and these hydrogens, when we are considering the cyclobutane ring as planar ring, then only this is possible. So in this case, the 2 hydrogens will be your homotopic. Another one will be your this one, where you can see the 2 hydrogens are present, and here they are interchangeable by I present in between. So here is a I. As you can see from this point, if you go this side and the back side, same. Similarly from CH3, the back side will be also CH3. So this is also enantiotopic. Right. Now let us see more examples. If you consider for this one, in this particular case, here you can see there is a chiral center present, that is this one. This center is chiral in nature, as a result of which they are near to chiral center, so they never can be enantiotopic or your homotopic. Finally, we can conclude that this will be diastereotopic. Next we have these 2 hydrogens. Can be written as like this. In this case, your carbon in the front will have this is your front carbon, so you can write it as chlorine upside, hydrogen downside, and the 2 hydrogens which are ticked can be written as here and here. So since you can see that there is a presence of axis of symmetry through this one, so these are enantiotopic. Now the last in this case is your these 2 hydrogens present. these are the two hydrogens. So if you consider these two hydrogens, a plane of symmetry here. So this plane of symmetry is your sigma. As a result, these two hydrogens will be also enantiotopic. Now we are going to see that two types of heterotopicity, if present, descriptor term arises. So let us see how. When the molecules are having only one prochiral center, that is before chirality. So that type of center is known as your prochiral center. So if you see here, we have two groups similar, that is chlorine and hydrogen. So this type of thing is known as achiral. But if you change one of the group, then it becomes a prochiral part. So we have exchanged the Cl with CH3. So this is a prochiral group. Now in this case, we will see the descriptor, how to assign the descriptor. So if you consider this one, first you need to find out the priority order. So let us start writing the priority order. So in this case only, you can see here that CH2OH, CH2OH, CHO and CH3 given. So first priority will be given to your CHO. Similarly, if you consider this is your target, then for this description we are going to consider this as B, and then this one will be your C and this one will be your D. So we are assigning the descriptor for this center. Now if we consider for this center, descriptor will be A, B, C and D. So for your right hand side, you will see that the rotation is in the clockwise direction, that is A, B, C. So this will be your pro R. When we are considering left hand side one, we have A, B and C. This is anti-clockwise. As a result, we will assign it as pro S, because we know priority order will be always A, B, C, right? So one of which descriptor is to be determined gets the higher priority always. Now we are going to talk about molecules having more than one prochiral center, and in this case we have this as first one, this as second center and this as third center. The above portion and the below portion we are going to assign as pro R and pro S. So if you consider here this group as A, this is B and this as the prior group C, then you can see that rotation is occurring in anti-clockwise direction. We can label this as pro S. So the below one will be pro R. We should always include the enantiotopic ligand to determine the prochirality of any hydrogen atom. So in that case, we need to find out the descriptors for the hydrogen present. Here you have this two hydrogen and we are going to determine their descriptors. This is our first prior group A. Next, the below portion will be your B, and if I am describing this hydrogen, this will be C. So it is clockwise direction. But remember, since hydrogen is present above the plane, the descriptor will be opposite to that. So we have here the descriptor as SS. Now the first S comes for this one and the second S comes from pro S. So the opposite one will be your RS, and the down ones, if we try to conclude what will be their descriptors, we can see here that this one will be A, this one will be B, this one will be C. So this is anti-clockwise direction, but since hydrogen is present above the plane, it should have been below the plane, the descriptor will be opposite. So here we are going to write down R for this particular hydrogen, and for the other one it will be opposite, and it would come to be as your SR. So this one is SS, this one is RS, this one is RR, and this one is your SR. Next we are going to see that molecules which will have some pro-pseudo-asymmetric center. So if you see here, this one and this group, though they look same, but they are going to have R and S configuration different. So first we need to find out their description, and then this one is our pseudo-asymmetric center. This is not a prochiral center. So for the first one, we have this group as A, this group as B, and the down portion will be C. So it is coming from A to B to C. So this is anti-clockwise, but since the hydrogen is present above the plane, so we need to find out below the plane. The configuration for this part will be your R. So the opposite configuration will be present here. So this one is going to come to be as S. You can also find out. So this is S. Now we need to assign the descriptors for these two hydrogen. So this will be considered one as pro R, and this is going to be considered as pro S, right? So how this occurred? Remember that priority is always given to R over S. So if I consider this as A group, next the below portion as B group, then this one comes as C. So from here A to B to C. So this is clockwise direction, but since hydrogen is present above the plane, so it is anti-clockwise, thus it comes or derives its name as pro S. If we see another one, then you can see here this is a stereogenic center, a chirotopic, as well as pseudo-asymmetric, and we are going to provide the descriptor for this one as R, and this one will be as S. So then also if you see here, since these two groups are different, so this can be concluded as stereogenic center. We cannot assign in this case your pro R or pro S. Next we have molecules having one chiral and one prochiral center. So for chiral center, you are going to provide a descriptor of R or S, and for the prochiral center, you are going to provide a descriptor R or S followed by the descriptor of chiral center. So in this case, if we consider this center, this will have a descriptor of R, A, B, and the down portion C. So it is coming as your anti-clockwise, but since hydrogen is present above the plane, we can conclude it as it is R. So this one is R. Now this hydrogen and this hydrogen. So consider one and find out. Then you can see that this will be your S, this will be your R, and since from here we can grab the R, so SR, and this one will be your RR, right? Next we are going to see molecules which have a prochiral axis. So we have already seen this type of allene type of molecule. So if we try to draw this, we are going to see that this can be drawn like this. Circular portion, this is your front carbon, chlorine upside, hydrogen downside. Then we have, if you consider this as HA and this as HB, then you have HA this side and HB this side. Again, in the same way, if you try to provide the descriptor, this will be your pro R and this one will be your pro S. Another category is molecules having pro-chiral plane. So this one is your example, and here we have a plane. In this case, this hydrogen and this hydrogen needs to be getting assigned with the descriptor. This will be considered as pro R and this one will be considered as pro S. Now we are going to see our last category, that is molecules having prostereogenic but a chiral center like this. So you can see this is your prostereogenic but a chiral center. In this case, you can see here one hydrogen is above, one hydrogen is below the plane. So if we consider this group as our reference point, then this hydrogen is cis to your this tert butyl group, whereas this hydrogen which is present below is trans to it. As a result, we can assign it as pro cis and pro trans. So this is our pro cis and this is our pro trans. Right? Last thing for which we are going to provide the descriptor will be the faces of the ketone or faces of the aldehyde. In that case, 2D chiral simplex we are going to take. Now, if you consider this particular aldehyde, then you can see that one face is towards us and another face is towards the back, that is behind the screen. So for top face we are going to assign the descriptor. If it is clockwise, then it is Re. If it is anti-clockwise, then it is going to be Psi. So for the first example, this is your A. This one is your B and this one is your C. So it is anti-clockwise direction. As a result, the top face is Psi and the back face will be just the opposite. So it will be Re. Next, for this example, this is actually a Propseudoasymmetric center, and here we are going to first provide the descriptor for the two centers present beside it in order to get the priority order. This one is coming to be as S and this one as R. This oxygen is considered as the first prior group, then R, then S. So the top face will be from A to B to C, that is clockwise direction, and since it is pseudo asymmetric center and pro-pseudo asymmetric center, so we cannot use capital RE and capital SI. Instead, we are going to use small r and small e. And for the bottom face, we are going to have just the opposite from this one. So for bottom, we are going to write SI, right? Now another example, if we consider this one. So see here, we have considered a chiral center while giving a descriptor. So here we have a diastereotopic plane where we have a chiral center. Along with that, we will assign the descriptor for the faces. So this particular group or this particular center will get the descriptor of R. Okay, and the top one, top face will be written as SI, Psi, and since we have a R as the chiral center, so we are going to write Psi R, and for the bottom face we are going to write RE R. So how this is occurring? Let us see. This one is your A, top priority group. This one is your B and this one is your C. So it is anti-clockwise direction. As a result, SI is coming, and for this chiral center, R is coming. So for the top face, we are going to write psi R, and for the down portion, that is below face, we are going to write down re R. So these were the three kinds of assigning the descriptor for planes present below and above your ketone or any kind of aldehyde. So this is the checkpoint. You are going to comment on the topic relationship of the two faces and provide suitable descriptor. Here ends the topic. So hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.